All right, guys, so I was just saying that today in lecture 8, we're going to be talking about enthalpy, internal energy, specific heat, CV, and C sub P. Remember, the V refers to constant volume, P to constant pressure. So this is the important part. CV, constant volume, P, constant pressure. Okay? And I said that this, generally, I can derive the term of enthalpy. I can do a derivation starting from one equation. But today, I think I'm going to just try to do it with a couple of sketches so that you can see really when you use one or the other. So here we're only dealing with closed systems. So the two possibilities you have for a closed system means that the mass within the system is constant. So you see that the mass over here is constant, no? All right. And the other case that we solve all the time is the one of the piston cylinder. Okay. So in this case, this will be the system. All right, so you have a constant mass. And now that I just mentioned, this is the V is related to the constant volume. So, and P to the constant pressure. So in this one, what do we have? In this one, we have constant volume, no? The volume cannot change within the system, which is the dashed line. In this one, what do you have? If you hit this, what's going to happen? As you hit this, it's going to be more pressure inside, but the pressure will remain constant because this will be able to move up, no? If you cool it down, it will go down, keeping the pressure constant. So this one will be the case of the constant pressure. All right, so this is the important part here to understand, really. This is. So just by saying that, you might have, probably you're already guessing that maybe in this case, you will have to use C sub V, and maybe in this case, you will have to use C sub P, no? So now that we know this, let's see what is really the difference between both of them. All right? So let's say in this one, you need to put heat. And the same thing for this one. All right, so basically here, in this case, the amount of heat that you need to put into the system is proportional to the mass, CV, times the change in temperature. And remember, CV, we say, is the specific heat. So specific heat basically means how much heat that substance can retain, no? Okay? So in this case, Janine, this is defined as how much, the way it's calculated is how much you need for 1 kilogram, let's say, of substance inside here to raise it 1 degree. That is really the value of the CV. Okay? So a constant volume, the amount of heat you need to put to raise, let's say, 1 degree will be equal to this one over here. All right? But for this case, the Q will be equal to what? The mass C sub P delta T. So here pay attention because you have the same amount of substance, okay? All right, the same amount of substance, but here the volume is fixed and here the pressure is fixed. And these values are not going to be the same. Okay, you don't put the same amount of heat here to raise this one 1 degree as you put over here for the closed system. All right. Okay, so let's do the derivation of this one here very quick. Basically, in this one, knowing this, if you use the first law of thermodynamics, which is what? Heat minus work equal to the change of internal energy when you neglect kinetic and potential energy. In this problem, you see here, there is no work done by the system or done on the system or anything. So really, this is 0. So this will give you that Q is equal to the change in internal energy. And this is equal to M C sub B delta T. Okay, so now you're going to see the difference with this one. So this is the important part. If we do the same thing, here we start from the first law of thermodynamics. Let me start over here. Q minus work equal to the change in internal energy, okay? Neglecting kinetic and potential energy. So now, is it any work done over here? Yes, here you have the work done by the piston moving up and down, no? And if you remember, the expression for the work done by the piston at constant pressure is P V final minus V initial, okay? So I can just rewrite this as follows, that this is equal to Q minus P dV, which is basically V final minus V initial, will be equal to delta U. So I'm just going to put here work equal to integral P dV. For constant pressure is equal to P dV. Okay, V final minus V initial. And here I'm just going to say that delta U, I'm going to say is equal to du. It helps for the derivation, okay, on the next step. So here I can say now that Q is equal to du plus P dV. Okay, I'm going to do one step now and then I will do the derivation. So now, this term over here, so internal energy, du is internal energy, PdV is work done by the pressure. This term over here is what is known as delta H, which is the change in enthalpy. So H here is enthalpy, okay? And this term here of enthalpies, actually here you see you have delta U equal to mCV dt. This will give you that Q equal to the change in enthalpy, and this is equal to what? M C sub T delta T. All right, so let me finish and then we do a little summary. So basically we have H, which is the enthalpy, is equal to what? Is equal to U, if I don't put the, if I remove the DH, plus PV. So the definition of enthalpy is what? Is enthalpy if you just read this equation, what is this? This is internal energy. And what is this term? This term came from this one here, no? Which is work done by pressure. So this is work done by constant pressure. You want part. I don't put constant, but basically it should be the term constant. Okay, so let's go back for a second. In this case, the piston, the volume, the system is closed, but the volume is constant. Okay, so in this case, what do you use? C sub V. If you have a closed system, but now the mass is still constant, but this is a piston cylinder assembly. So now what happens is that there is the pressure is constant. In that case, the Q or the delta H would be equal to what? mCp delta T. And the important part is here. You see what is the difference? Is that in here, because it's fixed, there is no work done by this moving part, which is the piston. Yeah? In this case, because this is moving, you need to add this term over here. Okay? Okay, one thing I'm going to do a little detail here because maybe you are asking your question, how can I go from here to here? All right? So maybe let me just do that in detail. So note over here is not that important, but I want to do it because I know I don't use much the textbook. So let's say you have H equal to U plus PV. Okay? So what would be DH? What I'm trying to show is that this over here is equal to this, okay? Ready? Okay, if you take the derivative of this, that should be equal to what? Du plus dP times V. The derivative of, let's say, uv is u prime v plus uv prime. Okay? So the derivative of this, you first derivative p and you leave v constant plus what? P dv. Okay? But what is the condition that we are using over here? Is that P is constant. So if P is constant, what does that mean? That the value dP should be equal to 0. Okay, if you take the derivative of a constant value, you get 0. So all this term is 0. So at the end, you end up with what? dH, which is what we have over here, should be equal to what? du plus pdv. Okay? Basically, in between this line here and this line really should be, I should be doing this, okay? But I didn't want too much information over there. Here, I just want you to get the concept, is that constant volume, CV, constant pressure, CP, and that the difference comes because this is internal energy plus work done by pressure, and that new term is called enthalpy. Okay? Okay, if you want, I'll show you the derivation. I have it here on the page. You know you have access to all this stuff online. All this stuff is online on the videos that I put. So yeah, this is actually comes from there. So if I do the derivation, this is when you do the derivation, is that for an ideal gas, let's say you use this equation of state, which is PV equal nRT, okay? So you see this equation means what? And this is good because this will explain to you why we need to use tables, okay? So you see over here from this equation, what are the different properties? We have pressure is a property, volume is a property, T is a property, no? Let's say N and R could be constant. So basically here, we have a function, which is in function of how many variables? 3. P, V, and T, correct? So if you try to solve for P, the answer for P should be in function of 2 variables, volume and temperature. If you try to solve for V, it would be in function of pressure and temperature. Okay, if you try to solve for T, it would be in function of pressure and volume. Okay, so that's the problem. Is that generally in calculus, what you learn to study variables, to study functions in function of 1 variable. Okay, but what happens if you have a function in function of 2 variables? So let's say Q over here, there is no work for this system, and let's say Q equal to delta U or du, and du is in function of temperature and volume. So if I do this, I first take the partial derivative of u with respect to t, I keep t constant, and then I take the partial derivative of u with respect to the volume, and I keep the volume constant. I mean, again, just follow quick, you don't need to understand this. In this case, what is constant? The volume. So that means that dV is equal to 0. All right? So now you see then that Q is equal to the partial derivative of the internal energy with respect to the temperature at constant volume times dt. It happens that this variable here, CV, or this one here, is equal to CV. Really, this is equal to CV over T. So the amount of internal energy you can absorb at constant volume using temperature. Okay, you see what CV, the mathematical definition is? This is what it will be. So really, you see, this is CV. Okay, and then I can do something similar for the other one. But what's important over here to realize is what? Is that one property is not in function of one variable. One property is in function of two variables, okay? So if you think about it, the value of one property is in function of a function of two different variables. So if we want to find the value of the property P, we need to look at the variation of the property P with respect to the volume and the temperature. So that means you end up solving this type of equation. This type of equation is a differential equation. So if you want to see the variation of one property with respect to other two, you should be solving every single step a differential equation. So instead of solving a differential equation, what we do in this class is that we go to tables where for two different values of V and T, they already give you the solution to the differential equation. All right. So personally, I don't like tables, but the alternative is a lot worse, no? Which will be to be solving differential equations all the time. So I just want to let you know that at the end of the day, the fact of using the tables is not that bad. Okay? And when you go to the tables, what do you think you're going to need? You're going to need to know two different values, no? Because these two different values will help you to solve the pressure in this case. These two different values will help you to solve for the volume, no? And so on and so on. So that's why when you go to the tables, you always have to look at two different values. It's like a table. You have to look at the X, the Y, and you will point the point over here, no? They're trying to find. All right? So again, this is not going to write it, but I'll show it to you. Okay. So now I'm going to talk about specific heat relations. Okay, so again, repetition is learning. So let me just redo the same figure again. So in this one, we know volume is constant. This one, we know pressure will be constant. In this one, we say that Q was equal to change in internal energy and equal to mc sub v delta T. Okay? In this case, we say that Q was equal to change in internal energy plus PdV, and that this was equal to the change in enthalpy and equal to mc sub p delta T. Okay, and this is basically the Q over here. Okay, so imagine over here that you have a substance inside that you want to raise by 1 degree. And this one, you have the same amount of substance you want to raise by 1 degree. Which one do you think is going to require more heat? The one where the volume is fixed or the one where the volume can move but the pressure is constant? So probably it's going to be this one, no? Because really you know that if it's fixed, you heat this. If the volume is constant, the heat is going to make the particles to move faster. They're going to hit each other, so they're going to heat, no? Faster. If here the volume can change, it's going to take longer for those molecules to start hitting each other and increase the temperature. All right? So you could guess over here that the amount of heat needed to raise this one 1 degree is going to be higher than this one. So you could guess over here that Cp should be higher than Cv. Okay? So in the book, they use the variable K, but if you go to many aerospace textbooks for aerodynamics, they call it gamma, which is the gas constant. All right? The definition of this, that's why I do this, is change in enthalpy divided by the change in internal energy. So by definition, you see here that the change in enthalpy is equal to what? mc C sub P delta T, and that the change in internal energy is M C sub V delta T. So you can see right away that this is going to give you that K or gamma equal to Cp over Cv. Okay, and this will be, if you want, called the specific heat ratio. Okay, so again, you could see that if I do the derivation, but I'm not going to do the derivation, the relation between the Cp and the Cv, we say that the Cp needed to be higher than the Cv, is actually equal to what? It's equal to Cv plus R bar over M, where R is the universal gas constant, so this will give you that Cp, or Cp is equal to Cv plus R, okay? So using these two equations, it's very simple now. You can say that K or gamma equal to Cp over Cv. What is Cp? Is Cv plus R divided by Cv. So this will give you that K times Cv is equal to Cv plus R. So if we solve for Cv, this gives you Cv, I'm not going to skip any step, will be equal to what? K minus 1 will be equal to R, which will give you that Cv is equal to R divided by K minus 1. Reason I'm doing this is because on the last problem or last class, they were using this relation in order to find Cv, okay? So I want to tell you from where it's coming. Okay, and if I do the same thing now, but solve for, instead of Cv, I solve for Cp, what do you have? K equal to Cp over Cv will give you what? Cp Cv, I could just put this one here, really. So Cp, Cv, so let's do the division. Cv here will be Cp minus R. So this will give you K, Cp minus R equal to C sub P. If you factor out by C sub P, it's the same procedure. You get K minus 1 equal to Kr, which will give you that Cp. It's basically equal to the same as the other one, but Kr divided by K minus 1. So personally, I don't like to use these equations here, but you're more than welcome to add them to that page where I told you can add the units, okay? Sometimes in the problems, personally, when I'm the one writing the problems, I will give you the values for the CVs and CPs, okay? All right, because I think it's a waste of time to do this. Doesn't bring anything to an understanding. To me, the understanding is this, to know which equation you need to use. Know that it takes you time. Instead of giving you the value for CP and CV, they give you the value for the specific heat ratio, no? That you need to do the calculations. I don't think it brings anything to the understanding. But on the homework and so on, you might have to do some of this. All right? Okay. All right, so this problem that I'm doing today comes straight from those class notes that are online. Generally, I try to pick different problems, but I think this time this should be a direct application of what we just studied, this part over here. Okay, this part over here is the important part over here. And that's the reason why I do this example, because I think it's actually, I made this example just for this chapter. So I show you the problem that we don't have to write it down. So example, and if you want, I'll give you a few minutes to copy it or can read it. And we do the figure together. So Fn contained in a piston cylinder arrangement. So if you solve the problem of the exam, this is what I want to see. You do a piston cylinder. Okay, this is not a waste of time, okay? It gives you time to think about the problem. So you know it's a piston cylinder assembly, so right away, what should come in your head? This is a closed system, and if nothing else is happening, you know that the pressure should be constant, no? All right? Undergoes a constant pressure process, obviously, is a piston. Okay, I should actually remove the undergoes a constant pressure process. You should know that. All right? From an initial temperature of, so let's say here, T initial is 50 degrees Celsius. Okay? If you want, I will do here, we'll go through a constant process, through a constant pressure process from this one to this one, to a final temperature, T2, equal to 100 degrees Celsius. Determine the amount of heat per unit mass necessary in that process. So basically what we need to find over here is Q over M. Okay? So the idea is to solve the problem in two different ways. Okay, so the first thing we're going to do is what? We're going to use the equation for first principle of thermodynamics, which is what? Q minus work. If we neglect kinetic and potential energy, this would just be equal to the change in internal energy. Delta U or du. All right? So we're trying here to solve for Q. And in this case, what do we know? Work equal to PdV for constant pressure. This is equal to PV2 minus V1, or what I called before PdV. All right, so here we're trying to solve for what? For Q. So Q will be equal to what? du plus work. What did we just learn? Is that du will be equal to what? mCv delta T, no? Constant volume. So this will be m CV, instead of using delta T, I use dt, plus PdV. All right, so over here we need to solve for Q per unit mass, Q over M. So we have this M here, but let's see what we can do over here. Do you remember what is the definition of specific volume? Every time you have the term specific means per unit mass. So here this will be volume over mass. Okay. Okay, so I just got a good question. Is that why am I using CV here? It's because I want to solve it two ways. First, using CV, and then I will solve it using CP. But I think if we do it both ways, it's going to give you a better understanding of really what is happening. Okay, that's the idea. Okay, so you remember specific volume is volume over mass. So what does that mean? That we could take this equation here to write volume equal to mass times specific volume, no? Okay, so that means that I could rewrite this term over here. This would be equal to m CV dt plus what? P, and now m is constant because the mass is constant of the mass in this system, m, but what will be changing will be the specific volume dV. So now we have the m on both sides, and I can just write Q over N, which is what I'm trying to find, equal to what? CV dt plus P dV. Okay, or to just write Q over M, if I expand it, equal to CV T2 minus T1 plus P is constant, no? V2 minus V1. And this is actually what I tried to do yesterday with a problem that ended up having some numerical issues. What did I do? I said, now, if I use the ideal gas relation, which will be what? PV equal RT. This is the ideal gas relation. From this equation, we can find that V is equal to what? RT divided by P. Okay? So now if I go and substitute into this equation, so substitute into this equation, what you're going to get? Q over M equal to CV T2 minus T1 plus P divided by R times what? T2 minus T1. Yeah? The V, this becomes T. I just put this outside. R should be P. This should be P, and this should be R over here. Yeah, sorry for that. What I was trying to say is that the P will cancel out. Okay? I mean, and this is good. Actually, I told you initially that I wasn't going to do the derivation, but I think I ended up doing the derivation. What is at the end the definition of CP? What was the definition of CP? Is equal to CV plus R, no? I told you I'm not going to do the derivation, but actually this is what I'm doing right now. So over here, if you just rewrite this, you end up with what? CV T2 minus T1 plus R T2 minus T1. Or this would be equal to what? CV plus R times T2 minus T1, or which will be the same as writing Q over M. What is this really equal to? CP, no? And this will be CP delta T. So you see, I wasn't planning doing the derivation, but I ended up doing it anyway. So okay, but if you want, you can use the value for CV and R, but you end up with the same thing, no? Yeah. Okay. So let's say, let's call this expression here A. All right. And now, I mean, I don't know if we need to put values. If you want, we can show values, but you like to see values. Okay, and second solution, the second solution as one of you clearly mentioned, is that if we have our piston cylinder assembly, constant mass, P constant, you know, by definition here, what could you do? You could say that Q minus work. So basically, I'm just redo the derivation if you want. Is equal to this. What is the work? Maybe let me go here. This will give you that Q is equal to du plus work, okay? And work is, I mean, it's the same derivation plus PDV. By definition, H is dH is what? Du plus PDV. I'm just summarizing what we did before, so this will give you at the end that Q is equal to dH, that you know this should be equal to M C sub P delta T, which will give you Q over M equal to C sub T delta T. And obviously, we get the same thing for the two solutions, no? Yeah? Okay, so something that is also relevant to this, okay, I'm going to add over here, is that what? We know that Q over M, okay, here, forget about the Q over M. Let's go back to the initial equations. Let's see initial derivation. In this one, Q equal to the change in, for the closed volume. So for this system here, closed volume, constant volume, closed system, constant volume, closed system, constant pressure. Okay. So what you need to realize is what? Is that in this one, you're going to deal with internal energy with U, no? In this one here, if you want to go quick, you're going to be dealing with what? With enthalpy. Not with internal energy. So we had the equation when we did the first one on the first page. In this page over here, what do we say? Is that the Q is equal to the change in internal energy is equal to M CV dt. Okay? In this case, we have Q equal to m Cv dt or delta t. And in this one, we have Q equal to m Cp delta t. So over here, what I want you to remember or to realize is that every time you deal, is that not only here the volume is constant, but when the volume is constant, you're going to be dealing with what? With internal energy. And if you are dealing with internal energy, you will be using C sub V. Okay? So U, if you want, will be related to the C sub V. If you deal with a piston cylinder assembly where the pressure is constant, in this case, if you want to go quick in the problem, you're going to be dealing with what? With enthalpy. And every time you deal with enthalpy, you should use which constant? C sub P. So if you have H, you know that you need to deal with C sub P. Okay? But again, I go back to the other day's lecture. So basically here, all right, so I will put over here, this is very important as well. In this case here, we have delta U. This could be equal to what? Initial energy, final internal energy minus initial internal energy, correct? And this, what I'm saying here is equal to m C sub V T2 minus T1. So here, be careful. This equation here is always valid. Now, what did I do in order to derive this equation here? Let's see half the page. What is the additional equation that I considered? I considered what equation? The ideal gas relation. Okay, this is important, okay? This is probably one of the few things most important for this class. All right? So this is just valid for an ideal gas. An ideal gas, what is something specific about an ideal gas? Is that it always remains in the same state, correct? So this equation here is only valid for ideal gas, or what I like to call an ideal substance, because this actually can be expanded not only to ideal gases, but let's say you are dealing with a problem where you have this time water, okay? But the initial state of the water and the final state of the water remains within the same state. So for example, you can have water, but you might just be boiling, you might just be heating water from, let's say, whatever, 75 degrees Fahrenheit to 85 degrees Fahrenheit, no? In that range of temperature, the state of the substance water is still liquid, correct? So it remains on the same state, correct? So you could say that maybe the properties of the water within those two temperatures could be approximated by a constant value of the property C sub V in this case, okay? We're just heating water, all right? But now, for the same substance water, what happens if you go, let's say, from 75 degrees Fahrenheit to 250 degrees Fahrenheit? Now, the water changed state, no? Because you went above the boiling temperatures. You go from liquid water to gas water. So, can you use this expression? No. You need to use this one. You need to go to the tables and find what would be those U2s and U1 from the tables, okay? All right? But if it's an ideal substance without changing the state, that's what you will be doing. Okay, you can do this. All right. All right. So let's look at properties. Okay, so let's just remind a little bit some of the definitions we gave at the beginning. What is a property? A property is a physical characteristic of a substance. Some people will say of a uniform substance, but let's have a substance. So this can be what? Could be volume, pressure, temperature, etc., etc., etc. Okay. Now, the second definition, which is a bit the same, what is the state of a substance? The state of the substance is defined by the values of its properties. Okay, so liquid, water, or gas. All right, so over here, what's happening now? What is the state? The state of a substance can be liquid, gas, or solid, is defined. State is defined by its properties. Okay, so that's why we say that the state of a substance is divided by its properties. So if you are a different state, the properties should be different, no? And we know that states can be, let's say for water would be liquid, a mixture of liquid and gas, or this would be gas or vapor if you want to think about water and vapor. Okay, so the easiest example is always to look at the water. All right, so the water is liquid, you put it in a pot, you start heating the water. What's going to happen? The water is going to, the temperature of the water is going to increase. It's going to increase to a point where it's going to start boiling. But it's not like that. As soon as you get to the 100 degrees Celsius, all the water is going to be transformed in one instant into vapor, no? You still have liquid water as some of the vapor starts to evaporate. So that will be, when everything is liquid, will be liquid. When you have some vapor and some liquid, will be mixture, no? And then when everything evaporates, everything will be vapor. All right? So in here, the most important thing is a couple of figures that I told you that you could print and bring with you to other classes. I hope they are here, and I put them. This is the table, properties of pure substances, which is what we're doing now, okay? So this is good. So this is not the important figure, but let's look at the important figure. It's kind of similar, but it adds one more state. So this figure adds here the solids, the state solid. So in this area over here, the state of the substance will be solid, all right? Between these two curves over here, this system will be liquid. And in this area over here will be vapor or gas, okay? So if you look at this curve, we don't do any example in this case, but you see there's a way for the system to go from vapor to the solid state, okay? And actually, there's a very easy example that, and a very easy example is that what would be the easiest way to do ice? What happened here? I don't know why we got this. Let's see if that disappears. Okay, doesn't want to disappear. Okay, so what is the fastest way to do ice? Do you think it's from liquid water? Probably not. This will show you what. Let's say you have a boiling machine, okay? And you boil it until you have steam. And let's say you're inside the house, you live in the north, okay, when it's cold. So you want to do tea, you put your pot, you put it full temperature. And then what happens if you go outside and you let the vapor to go out? as soon as it's going to touch the cold earth, it's going to become whatever, snow or ice, no? And you don't have to go through the state of liquid water in order to get ice. All right, and that would be a lot faster, no? Yep. So that would be one example. But the important part of it is that this page here, you can print it. So please print it with you and bring it to every single class because it will help you. So basically what's important over here is that it will be these curves. I'm going to do something similar to these curves, okay? And I will rewrite all these expressions basically. But again, now, these two figures that we're going to do now are really the backbone for this class. If you get those two curves, you're not going to have any problem in using the tables. If you don't get this curve, you don't need even to understand both, you only need to understand one, okay? So if you remember before, we said that one property needs to be in function of two other properties, okay? So let's see if I do the curve over here. So which one did I have first, the TV or the PV? That way I follow the order. This would be the TV, okay. And this is generally the one I like the most personally. So let's say you have temperature. And here you can have volume or specific volume. Generally would be specific volume because that's what you get from the textbook. All right, and then you will have a curve. I didn't do a very good job, but some type of curve that way. And here, I'm going to do the case again of the boiling water. All right. So let's say you're at home, you want to cook pasta. Okay. In order to cook pasta, you need to boil the water, no? So let's say you are here at a temperature at whatever, that is room temperature. Okay. So what's going to happen? And you have a certain volume over here. So you have here. What's going to happen if you start boiling the water? The temperature is going to increase, 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 correct? Up to, let's say you're boiling water at a pressure of 1 atmosphere, okay? All right? Then you reach the boiling temperature. So let's say here will be T equal approximately, really is 99.97, I think it is, but let's say 100%. Then what's going to happen to the water? Some of the water is going to start to evaporate, but some of the water is going to stay liquid, no? So you're going to have here a process at constant pressure. So this area here will be liquid. The state of the water will be liquid, but it's just heating to basically 100 degrees. Here you will have a mixture of liquid water and gas. And then what will happen once all the water ends up finished to evaporate? Everything will be on the vapor or gas state, okay? And then at this case over here, this is constant pressure, the temperature will keep increasing. And again, this will be at P equal to 1 atmosphere. So basically, this figure is exactly the same as this one, but I just simplified. What is this curve showing? Is that this part here will be liquid, okay? Compressed liquid. This part will be liquid vapor. And this part will be superheated vapor. So what happened is that if you look at the tables on the book, maybe I'm just going to do this figure here. Let's say just this one, it doesn't matter, it's the 7th edition, but they will all be the same thing. There is no difference. Appendix tables. If you look at this table here, the first one, what does it put on top? I mean, properties, this is the only one of these, but this is saturated water, no? This is the only table. Really, you don't have tables for this, but in this case, saturated water. So saturated water means what? That you are on the state that you are in this area, no? Yeah? Then you should have a table. So table A3, what's the title of table A3? this is pressure constant, so table no E3. Let's see what will be the next table. Okay, yeah, so, all right, yeah, so that was correct. So what happened is this, is the next table, which is table A5, is superheated vapor, okay? So this one will be for what place, for which location over here? Let's see, camera. This would be for this area over here. Okay, so sorry for that, but basically just for that substance, they don't have tables for this region. They have tables for here, which is the superheated tables that we just looked at. This one, superheated tables, and table A3 and A2, which are tables of liquid vapor, okay? So you have tables for this area over here. I will show you what happens over here, okay? I will explain to this, but there's no tables for here, but you can get the values from here from actually these tables. So you have tables for here and tables from here. So if you do this figure and you know where you stand, you know which table to use in the textbook, okay? So that's why this is so important. So let me just add a couple of things here to this table, and I will stop over here. These 2 points over here, this line over here, okay? So this line between this point and this point here is going to be called the saturated liquid. So basically that means that this is liquid, and in this line at a pressure of 1 atmosphere, this would be the temperature at which the water cannot retain its state. Once you reach that temperature, there is so much heat that you need to change the state of the water, no? And then at this state, what will happen? Some will start to evaporate, okay? Similarly, this point over here, or this line, will be saturated. Let's see how they use on this table, gas. Yeah, they use saturated gas, okay? So this value here will give you, let's say if you calculate in this value, this will be the value V sub, okay, F, and this will be here V sub G. So V, so the F, sorry, stands for what? Fluid, and the G for gas, all right? So let's look at this figure. We say here at 1 atmosphere, let's say 1 bar, what is the temperature at which the water is gonna boil? 100, no? Okay, so if you look here at this table, which one is this one? This is the pressure table. So let's say we have water boiling approximately at 1 atmosphere, let's say would be 1 bar, okay? I think 1 atmosphere is 1.014 bars, okay? So what is telling you this? What is the saturation temperature? You were expecting 100 degrees, no? What is this telling you is that the temperature at which this is gonna saturate is 99.63, okay? Now, what would be the volume? The liquid, the V sub F, the volume at which this is gonna saturate would be 1.0432, actually will be 10 to the minus 3, because this is a 10 to the minus 3. So this will be 0.0010432, okay? So the value V sub F over here would be the 1 point whatever times 10 to the minus 3. And what would be the value for the V gas? 1.694. So this value here would be 1.694. So it's not that interesting for the volumes, but let's say you needed to find what is the value of the energy use of gas and use of fluid. If you go to these tables, you see you have similar values for saturated liquid or saturated vapor, no? So in order to the change of energy to transform all the water, if you want, between liquid and gas will be equal to what? 2,506, which is the one at the gas, saturated gas, minus the one that you needed to get saturated liquid, no? Which is 417. So let's say in the problem they ask you, what is the amount of heat that you need in order to boil, let's say, 1 kilogram of water? You will have, like the equation we derived, Q equal to M U final minus U initial, no? Yeah? So what will be the U final? U final will be that you transform all the water into gas, no? And the initial temperature was the initial temperature, if you want, that you use, if you calculate from this point, let's see. If you calculate from this point will be UG minus UF. If you calculate it from here, will be equal to what? UG minus UF minus whatever was the value over here of the energy, no? But let's just do it between this area here, okay? So basically, I stop over here today, and next time I do the other figure, and we start just doing problems so you can practice. So please, next class, print the tables and bring the tables. Is that okay? If you don't practice in class, it's impossible, all right, to learn how to do this.